bits per second, and megabit is actually 1 million bits, not the power of 2 that we use for RAM allocations and drive allocations. A 40-byte packet, on the other hand, is only 0.32 kilobits. So the smaller your exabyte packet is, the less bandwidth it takes, which should be obvious to everybody. For any given 100 megabit Ethernet card, which you can buy a colo server, dedicated server that has one of these in it very easily, very cheaply, $19.95 per month from Linode, for example, you can send every 14 byte Ethernet frame, which is the max frame size that you send, is 12.12 kilobits. If you send 82,046 of these per second, you're maxing out your 100 megabit line. So you have to send about 8,000 packets per second of full frames to max out 100 megabit. But if you go back and look at 40 byte packets instead, you'd have to send out 312,000 of those to hit the same 100 megabit rate. This is the reason why for most networking products, you don't see them talking about, yes, I'm a gigabit IPS. You're not a gigabit at 40 byte packets, though. You're a gigabit at really big, beefy packets you can parse slowly. No one's going to claim 100 megabits or 100 gigabits of 40 byte packet frames, just unless they've got crazy CPUs or hardware acceleration. It's not really possible to do that with a standard PC. And any vendors here who want to claim otherwise, or let me know how you do it. But for the most part, you can't really get beyond about 50,000 packets per second with standard PC hardware, because you end up hitting the interrupt limit of the card itself. So you just can't send more than 50,000 packets per second in most cases. And if you're receiving it and then resending it, you're in a position where you're actually handling 2 interrupts per second. So unless you have some awesome hardware offload on your Ethernet card, it doesn't really work very well beyond those rates. This is why in the network testing space, which I just came out of before I joined Rapid7, you'll see a lot of product vendors that have PC-based solutions, but you need an entire rack of them to get over a certain packet rate because of this limitation. So when you actually get down to what the numbers look like, any given decently fast Linux server on the internet can send about 50,000 packets per second. The bandwidth required per byte that you send of those packets is 400K per byte you send. So you're sending a 40 byte packets as fast as you can. 40 byte packets at 50,000 per second. You end up sending about, I think it's 1.6 megabits, and that scales all the way up. So this is important when you talk about how fast you can own the entire internet. So if you're looking at a standard TCP-based vulnerability, something where you connect to a service, you send one request to it, and then you shut it down, or you just leave it hanging, that takes about 4 packets. You have your SYN, you've got your SYN ACK, you've got your ACK, then you've got your data packet. Now, most TCP stacks can't actually handle these rates. You have to build your own custom stack to handle the send response of this stuff. And it's pretty easy to do that. It's not actually that big of a concern. But it only takes you 3.5 days to cover the entire allocated IP space with an exploit written this way. It's just not that much time. 3.5 days for one machine that you spent $20 for, that you probably got prorated for $5, you can actually send this much traffic. Now, if you have a single packet exploit, something like SQL Slam or another UDP-based vulnerability, like the ISS vulnerability from years back, it only takes you 19 hours to cover all allocated IPs with 50,000 packets per second. So if you're looking at how quickly you can own the entire IP space with one brand new exploit, it's awesome. You can basically knock out the entire internet in under 24 hours from a 1995 server you bought with a stolen card. So the risk is pretty high, just because the IP space is small, the packet rates are high, and a lot of the vulnerabilities that we find these days are really easy to exploit with small amount of data. A single packet targeted towards particular countries is even better, because the US only has about 1.5 billion allocated IPs, which is a huge percentage of the internet, but still not that big. It only takes you about 8 hours to send a single packet to the entire US. If you want to go after China, it's only 1.37 hours. If you want to go after Russia, it's only 10 minutes. And this is only using one machine. Actually, the problem you run into with countries like Russia is the IP space is small enough that if you start sending have multiple machines hammering it, you actually eat up all their incoming lines. And I actually ran into this not on the IP side, but on the telephony side with Warbox. When dialing Moscow, I accidentally overloaded a switch. So calls stopped happening for a chunk of Moscow. Just the infrastructure is not really there. So the same thing applies to the networking and the data side as well. So if you want to get all cloudy on this stuff, and I'm not going to get all beaker on you and tell you about the legendary clouds, but I will tell you that if you can allocate, so for the Twitter folks in the room, if you spend, let's say you go on Amazon EC2, you allocate 10 servers, you have each of these servers sending 50,000 per second, you can basically hit all of Russia in 60 seconds. It's easy. And the cost, the best thing about this is billing. This is the same reason why projects like Warbox were successful, is the telephone telephone providers, voice over IP providers bill you based on minutes. If your call doesn't connect, in other words, you're just sending your probe, you never get charged for it. And when you do connect, you're only paying a penny per minute you're on. Well, bandwidth rates with these cloud providers are pretty similar. They charge you based on gigabytes. You're not sending gigabytes. You're sending like a 100-byte packet with an exploit in it. You don't really care about gigabytes. So you look at how much money you have to spend to cover all of Russia, it's about $50 to do it in 60 seconds. So the numbers are just so low these days that if you have a credit card, an XDC2, and a really nice exploit, you can take out an entire country in 60 seconds. And it's not really hard. The space is small. So the point with all this is that because the internet is as dense as it is, because the available computing power to your average attacker has gone much higher, it's much easier to carry out large-scale attacks because the space just isn't that big. 4 billion isn't that big of a number when you have an EC2 cloud, or when you have 50,000 packets per second as your standard default send rate. And I'm flying through this. I'm going to try to slow down a little bit. So of course, going on to IPv6, this solves almost all these problems, of course, because IPv6 is the magic band-aid for the internet. The problem is IPv6 will never get rolled out in our lifetime, I'm guessing. Like, people will use it, but we'll still be using IPv4 20 years from now. I mean, it's not going to go away. Unless we start, doing large-scale firewalling or filtering or blocking, or we start making islands out of the internet, it's not going to go away anytime soon. What's probably going to happen is we're going to have lots of really big IPv4 islands that are interconnected by v6 backends, and we have some v6 routing on top of it. But it's going to take a really long time for this to happen. So the challenging thing for an attacker trying to attack you over IPv6 is the IP range itself is huge. You can't just scan. You can't just scan, .1 to 254 on the subnet and hope to find anything, because every host on the IPv6 is being allocated /64. Now, /64 is the current internet times the current internet in terms of space. So 4 billion squared is the number of IPs you'd have to scan just to be able to find one system that's been allocated an IP or /64 and IPv6. So you can't just scan for stuff anymore if you're not local to it. You have to depend on things like other services that'll tell you what IPs are available, DNS. You have to use things like SNP tables, all sorts of fun things, just to be able to find what's out there. So this has good and bad sides, right? I mean, the good side is you can't really just scan for IPs anymore and send an exploit to every IP in the internet in 10 minutes. The bad side is if somebody owns a box to your network, or they put their own rogue IP in the network, you will never find it unless you're local. You can do some local probes to detect it, but you can't remotely scan for it. So you're trying to find rogue systems on a site that's not local to your actual physical media, not connected to the same switch as you. You can't scan for the systems anymore via v6. So this will completely change the game in terms of vulnerability management, that kind of fun stuff. Fortunately, we never have to care about it because we're all going to die before people use v6 only. So congratulations. It's, assuming medical technology doesn't get much better. So a lot of legacy software doesn't actually bind to v6, which is also a nice security feature because a lot of your old daemons don't bind by default. There's some systems where Echo and Discard and kind of older services don't bind to the v6 address, but they do bind to v4. So there's actually some benefits to switching to v6 if you can get away with it. Then again, a lot of firewalls don't handle v6 properly either. I mean, you talk to most Linux admins. What's especially funny is you find folks who run Linux on a local network, and they tell you that, okay, this is a really secure server. It's our licensing server. It's our customer data server. We're going to filter out everything except for this one port. We're going to block it and everything else. But what they don't realize is they used Ubuntu, they used a new Debian, they used a new Red Hat that loads the v6 module by default, which means the box comes online, gets a v6 address, allocates it, and now you can scan for it easily just by doing a local ping to the broadcast address on v6, and then you can just hit any port you want because the admin didn't realize that to filter IPv6, you have to create an entirely different net filter rule. It's not even the same table. So it's a lot of fun to mess with the admins at various companies I've worked at by shelling in from v6 addresses and watch them look at the log and say, what the hell is this? I don't even know what this FE80::: thing address is. Like, okay, I got owned, I don't know how or what. What is this weird funny thing that I'm looking at? So basically, most host systems, most newer OSs are v6 ready. Most networks, the large-scale networks, are v6 ready for routing. But users have no idea how to use this stuff. Have you ever tried to put an IPv6 address into a web browser? It's a lot of fun. Just try to figure it out sometime. I'll give it away. That you put it in square brackets. So HB:// square bracket, some ungodly long IP address. And if it's a local IP address, you have to actually put the Ethernet interface ID into the URL as well. So it'll be your IPv6 address, %, your interface ID in Windows, or your Ethernet device name in Linux, followed by a close bracket, then the IP and the port or whatever. So then the port. So the funny thing about this is most browsers don't support the local scope ID, so you can't even browse to local, most browsers support v6 but don't support local scope IDs, so you can't even browse to local machines. Anyway, so I won't rant too much on v6, but it'll fix everything if we ever switch to it, which we won't. So that